Today's talk will be more focused towards the islanding, as I have seen in the very first day of this faculty development program. Professor Bhalja discussed a bit about digital protection of microgrid. So I will not be going in that direction. Rather, we'll be discussing islanding phenomenon a bit more. Okay. So let me first share my screen. Please let me know if it is visible. Is it visible? Can you please confirm? Okay, okay, okay. Okay, maybe it will take some time to load. Uh, is it now? Okay, then let me try to share it again. Is it now? Okay, but it's showing that it is. Yeah. Okay, okay, okay. Thank you so much. Okay, so today's talk will be focused towards the introduction of microgrid and why it is required, and what are the main protection challenges, and then islanding, what is islanding, how we can detect it, and so on. And these are the outlines for the today's discussion that includes requirements of a microgrid, and then what are the challenges in terms of protection, and what is an islanding detection issue, why is it required to be detected, and how we can detect it. Actually, there are several methods available for that. And then we have to analyze the performance of different islanding detection techniques and what are the factors over which we can analyze the same. Okay. And then what to do after detection. Once you have detected the islanding, then what are the actions those can be considered appropriate uh, after detecting the islanding. Okay. And then to summarize the discussion. And then of course we'll be having session. Let me try. Mm, it's not there. Actually, in between, I will try to have some annotation on this. So that's why. Is it okay now? Means almost it's full screen. Other- Okay. Is it fine now? Or should I share the PPT itself? Actually, I have converted it into PDF. So better to share that. Let me try sharing that PPT. It worked in the morning actually. Oh, okay. Is it not visible to you only, ma'am, or anybody else is not able to see? No, not okay. 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 Let me try opening the PPT. Then please let me know if it is visible. Is it now? Okay. Okay then. Thank you. Let me full screen. Okay. So these are the outlines for today's discussion, and then first question arises that what is the requirement of a microgrid, or we can also say what the microgrid is actually. Okay, as you can see in this diagram, there is one circle corresponding to the microgrid, another corresponding to the utility grid. This circle is actually a distribution system that consists of different types of loads, household loads, industrial loads, and like that on. Okay. Apart from that, small generations are also attached to the same. As you can see, there is dedicated energy source, which includes this wind as well as solar generation. And then, since due to the variable nature of these resources, we have to have some storage. Also, battery energy storage you can see in between. And then, since the voltage provided by the battery will be DC, that is direct current voltage. So you have to convert it into AC, that is our conventional system. So you have to have smart inverters in between. Okay. So renewable based generations are there, battery storage is there, and then you have smart inverters. Okay. And that is connected to your distribution system and not the transmission side. Transmission side. Okay. This system was earlier a passive system when you were not having all these things. Okay, only the loads were there. These loads did not have any energy source, so it was supposed to be a passive system. But now, in the presence of these renewable generations and battery energy storage, this entire network has become an active network. It is sometimes possible to operate this distribution system in an autonomous mode. Okay, and this active distribution system can be called a microgrid. Okay, which is consisting of small generations that can range between several kilowatts to a few megawatts. Okay, so n number of generations you can attach to the distribution side, and sometimes you may be able to supply your local load, and whenever it is possible, then you can operate this microgrid in an autonomous mode, or we can say in islanded mode. Okay, there you can see there is a switch in between the utility grid and the microgrid. This switch, whenever it is open, we can say that the microgrid is islanded. Whenever this switch is closed, we can say we are operating this in a grid connected mode. Okay. Whenever this switch is closed, that means the voltage and frequency of this entire distribution system is to be taken care of by the utility grid. And these renewable based generations are supposed to inject the power into the distribution system without worrying about voltage and frequency. Okay. But whenever you are islanded, That means the utility grid is no more available. In that situation, this dedicated energy source, or we can say distributed generation, has to take care of the voltage and frequency. So whenever there is an islanding event, you have to detect it as soon as possible and have to change the mode of operation of distributed generation. That is one of the aspects of detecting the islanding. Okay. Second, if you do not have sufficient power generated at the local end with the help of distributed generation, then what you can do, you can disconnect your distributed generation, or we can say DG. Okay, if you do not have sufficient power, you just disconnect the DG so that the sensitive loads may not get damaged, because there is some requirements that the voltage and frequency should lie within these limits. Those limits we'll be discussing later on. So that is a brief about the concept of a microgrid. Okay. Now, what is the requirement of a microgrid? Now, as you can see, there are a lot of electrical loads, and more loads we are adding to the system. Nowadays, you can see electric vehicle is also there. So it is to be charged. And from where you can charge it, obviously you will connect it to the system or the distribution system to charge the batteries of the electric vehicle. There are a lot many modern loads which were not there earlier, say for example air purifier and so on, electric machine like that. Okay, now when you increase the load, you at all have to fulfill the demand of the load demand. Okay, now how to meet this increasing power demand? There can be two ways possible. One, you install bulk power generating stations, and those stations will be far away from the load centers. When they are situated far away from the load centers, what you have to do, you have to transmit that power from the generating station to the load centers. And that is possible with the help of transmission line, and then there is obviously a distribution system. Okay, so those transmission lines, either you build new transmission line to carry that huge amount of power generated to the load center, or what you can do, there is another option available. You can incorporate fax devices to the existing transmission line. What they do, these fax devices alter or manipulate the electrical parameter in such a way that more power can be pushed through the existing transmission line to fulfill the increasing power demand or the load demand. Okay, so these are the two ways. Obviously, building a new transmission line will not always be economical. Rather, to use the fact device will be a cheaper solution. Okay, and most preferred solution. And this we have to take care that the power pushed through a transmission line should never reach its thermal limit. That is to be taken care of. It is not that we can push any amount of power through any transmission line. There is one thermal limit always, and we have to keep the maximum transmitted power far below the thermal limit. Okay, so those are one aspect. That is one aspect, that you build bulk power stations. Another concept can be to have several distributed generations rather than having a bulk power station situated far away from us. These distributed generations or DGs can be placed close to the load centers and can be connected to the distribution system itself. Most preferred DGs are based upon the renewable power generation. Those renewable power generations mainly can be solar based DGs. You just convert sunlight into an electric power. Micro CHP based DG, what micro CHP is, this combined heat and power will actually enhance the efficiency of conventional thermal power generation. Okay, and then there is wind turbine based DGs. The problem with this wind turbine based DG is that you cannot place it anywhere. There should be proper place to install such kind of generations. And then there is biogas based DG, that is actually in function at several locations. If you see, the best place or the better place is to have these kind of DGs um, close to the hostels in several institutes, because there you may find a lot of bio waste. So that waste can be utilized. So that will be proper place. So biogas based DGs can be installed close to the load centers, no problem. Similarly, there are several other renewable energy based DGs. So these are the preferred DGs. It is not like that you have to install only these kind of DGs. There is several diesel generator based distributed generation as well. That was the earlier backup system. Okay. So out of these two concepts, one installing bulk power generation, another installing distributed generation. Obviously, having distributed generations will give you more advantages. Why? Because by doing so, you are actually reducing or eliminating the transmission losses. When you install a bulk power station and then transmit the power to the load, what happens? There will be transmission losses. But when you install distributed generation, those transmission losses will not be there and your electricity will be much cheaper. Okay. And several other advantages are also there. Why renewable energy based DGs are preferred? Since you know declining availability of fossil fuel, it is there, and then it also reduces the environment pollution. Obviously, then you can reduce the global warming, and thereby you may improve the public health. So these are a few reasons, um, so that you may prefer the renewable energy based DGs. Okay. Everything that comes with the advantages will also have several challenges. Here you can have the advantages like significant energy security, economic benefits will be there in terms of cheaper electricity, and it may also reduce the burden on the utility grid, so that grid may switch off several stations as per the requirement. And the challenges are, as we discussed earlier, that protection challenges will be there when you have DG concept, and simultaneously another issue is islanding detection issue. Okay. What is the definition of microgrid? A small network of electricity users with a local source of supply that is usually attached to a centralized national grid, but should be able to function independently whenever it is required to function it to operate it independently. It should be able to do so. Okay, here a small network of electricity users is nothing but distribution system or distribution network. Local source of supply is nothing but your DG or distributed generation. Centralized national grid is nothing but we call it utility grid or main grid. In India, it is your power grid. Okay, this provides you energy surety. Why? That can be uh, that we can understand next. This was the earlier energy surety approach, where you install diesel generator backup system at each household. Whoever is required, whoever requires the energy surety, that has to have backup system in terms of diesel generator was there. So whenever the utility grid is gone, say the supply is interrupted, what you have to do? You have to start this diesel generator backup system, and this will obviously be supplying either all the building, all of the loads, or the critical loads. Critical loads are to be supplied 24/7. So to supply them, you have to have backup in anyway. Okay. So whenever this is gone, that means you can start this backup diesel generator. Now, traditional is gone. Nowadays, you may have renewable based generations along with the traditional backup system. In this diagram, you can see there is one diesel generator system that was the conventional one. Along with that, what we have installed, solar based power as well as storage system is also there, usually which is battery energy storage system. Okay. With this, what is there? Normally, if you do not have much of the generations through this solar based power system, you can take consume power from this utility grid, this one, or the substation. Okay. Now, whenever this primary source is not available, what you have to do? You have to manage with these three. Okay. Let's say you have sufficient solar based generation. Then what you can do? You need not to start this diesel generator based system, and the load can be supplied through this. Okay. Now, say if you require say 10 megawatt for supplying these three buildings, then what you can do, if you have 10 megawatt generation, that can easily be supplied without taking current from the storage. If it is 9 megawatt generated and your energy storage is able to supply that 1 megawatt and is additional for several hours, you can use these two to supply your loads. Now there can be condition where you do not have sufficient power generated out of this, nor you have sufficient storage, then you have to start obviously this backup diesel generator system. So there are three things to support your backup, to support the requirement, to fulfill the requirement of the loads of these three buildings. Okay, instead of that previous diesel generator backup system, and that will obviously be polluting the environment as well. So our aim is to reduce the use of this diesel generator backup system. Okay. Now understanding this, how we are consuming power or we are supplying power out of the DG. Okay. We have converted all the load, all the distribution system load into its equivalent RLC parallel circuit. Okay. Let's say at any moment, this is drawing active and reactive power, which are PL and QL. Okay. So the requirement in terms of active and reactive power can be fulfilled partly from the grid and partly from the DG. Okay. So that means this, if we talk about active power, this PL will be nothing but PDG plus delta P. Okay. That is also written here. Yes, with DG. Okay. If you take out PL here, this will be delta P plus PDG. Okay. Why we have kept this delta P? The grid is supposed to supply only the difference between the DG power and the load power. If this DG power is perfectly equal to load power, that means this delta P will be zero. No power is required to be drawn from the utility or main grid. Okay. So that is why we have kept it intentionally delta P and delta Q. Now suppose if you do not have any power supplied from the DG, that means PDG is zero, QDG is zero. So without DG, the equation will become delta P is equal to delta PL, delta Q is equal to QL. Okay. That means all of the power requirements are being fulfilled through the main grid. Okay. Once you connect the DG, part of the supply will be delivered by the power will be delivered by the DG. Okay. So this delta P will be reduced, as you can see. Earlier delta P was equal to PL, now it is PL minus PDG. So this concept of distributed generation is actually reducing the burden on the utility grid. With this privilege, the utility grid or main grid may manage in an efficient manner with the provision of distributed generation. Okay, so that is the uh, concept. By utilizing, we can reduce the burden over the utility grid. Okay. Now, reasons for connecting a microgrid to a main grid, it is preferred actually to connect your microgrid to the main grid. There are several reasons. First, availability. Highly available power grids may act as an additional source for microgrid. Okay, so the availability will be a factor. Then operation and stability. Direct connection of AC microgrids to a large power grid facilitates stable operation, but only if the power grid acts as a stiff source to the microgrid. Okay, that means you need not to take care of the voltage, neither voltage nor voltage stability. It is to be dictated by the utility grid. When using renewable energy sources, a grid connection may allow reducing the need for energy storage in the microgrid. Earlier, what we have seen that along with the solar generation, we have to have a storage. Now, if you are connected to the utility grid and you have some generation out of the solar, so the difference between the load and the DG will come from the grid itself. You need not to require to install a storage system. That difference will come from the grid rather than the storage. So no need to spend on the storage system. That is another aspect. If not all the loads in a microgrid are critical, a grid connection may allow to reduce the investment in local generation. The same thing which was there. See, this battery energy storage system and this diesel backup system, if you do not have these two, you can save a lot of money with the provision of connecting it to the grid. If your grid is reliable enough and you do not have critical loads in these buildings, you may not spend on these backup systems. Okay, and you can only install this solar based generation and you can save the money. Okay, and then economics, obviously economically you will have several advantages or benefits. Microgrids are typically planned with extra capacity with respect to the local load. This extra power capacity you can inject it back to the grid and you can earn something. Okay, so it comes with economic advantages as well. Grid interconnection allows to reduce fuel operation costs by using the grid at night when electricity costs are low. Okay, instead of switching this backup generation, okay, you may consume this supply at night and during the hour you will have sufficient power generated out of this. Okay, so that is a few economical advantages if you have grid connectivity available. Okay, so it is always preferred to connect your microgrid to the grid rather than operating it in an autonomous mode. Obviously, this microgrid is key to smart grid. As you can see in this diagram, there are several buildings. Those buildings are smart buildings. You may have smart homes where you can install solar-based generations at the rooftop, and all the generation, all the load information will be shared with that of the utility with this. Okay, as you can see, Wi-Fi kind of signals at the top of the house, at the top of the building. Simultaneously, each and every component will be communicating with the utility grid or utility operator. Okay, so when you have the concept of microgrid, all the information will be shared with the utility grid. With that information, this utility grid can manage accordingly, and that management will give you a lot of economical advantages. How? See, whenever you have the information that electricity will be cheaper during say 12 to 1 or 12 to 2, what you can do, you can you can use your loads which are not critical, or which you can operate at any hour or at any time of during the day. Okay, say you have to wash your clothes, and then you can use washing machine during that hour when you have cheaper electricity available to you. So that information will come from the utility side, that during this hour you can you will be charged a bit lesser than the other time of the day. Okay, so that kind of management will be available. Simultaneously, utility will grid will also have the information of load, that what will be the load during 12 to 1 or 1 to 2 or 2 to 3, and accordingly it can operate several substations or switch them off as well depending upon the load requirement. Okay, so overall, smart grid is a concept for transforming the electric power grid by using advanced automatic control and communications techniques and other forms of information technology. Okay. Simultaneously, smart protection will also be there. Automatic switching off and on will also be there. There are several standards you have to take care of when you talk about microgrid or distributed generation. It is not that you can connect your distributed generation to the system without taking care of anything. Okay. The main provisions of this IEEE 1547 standard is, it is actually for the distributed generation or interconnecting distributed resources to the electric power system. So main provisions are IEEE 1 standard 1547.1, which is corresponding to test procedures for equipment interconnecting DGs. Okay, this distributed resources, we can also call it distributed generation. With electric power system, you can call it the grid or the utility grid. And IEEE 1547.2, it is corresponding to interconnection. IEEE 1547.3, corresponding to monitoring, information exchange and control. Point 4, it is IEEE guide for design, operation and integration of distributed resources and island systems with electric power system. And there are several more. Okay. So say 1547.5 has not been issued yet, and then 1547.6, it recommends practice for interconnecting distributed resources with the EPS. Okay, and like that. Now, what are the requirements in terms of voltage? As you know, you should connect the distributed resources without causing voltage fluctuations at the PCC greater than plus minus 5%. So those fluctuations should not exceed this limit. Okay. Here, PCC is nothing but point of common coupling, where you are actually connecting your distributed generation or the renewable based generations. Okay. And this LAPES is nothing but local area power and energy system that must not be energized, that must not energize the main grid when the main grid is not energized. That means whenever the main grid is not available, you should disconnect the local network out of the main grid as soon as possible. Otherwise, what will happen? The reverse current flow will be there, and it will be like that. You are going to supply the entire network, and that at all is not possible. Okay, so once you detect the islanding, you just have to switch it off, or you just have to disconnect yourself from rest of the network, because islanding may happen due to fault at any location of the system. Okay, so you do not know that location, so what to do? Immediately you have to identify that islanding has occurred and disconnect your local network as soon as possible. you can see this diagram. Let me go to that diagram once again. This one, okay. This is your utility grid, which we have represented by just placing a tower. It's not like that. There will be structure of lines, interconnection of several lines, and at any location there can be fault, and any circuit breaker may trip, may disconnect you from the sources, active sources, but there can be several distribution systems connected to this utility grid. And if you do not switch it off, you will be going to you will supply all of them altogether. So immediately you have to detect the islanding and switch this, and this switch should be open. Okay. Going back to the standards. Yes. Each distributed resource, a unit of 250 kV or more, aggregate of 250 kV or more at a single PCC shall have provisions for monitoring its connection status, real power output, reactive power output, and voltage at the point of DR connection. Okay. A visible break isolation device must be located. Even though if you have power electronics based switches, a visible isolation should also be there. Okay. A visible break isolation device must be located between the earlier that voltage at PCC should not fluctuate between more than plus minus 5%. There is some recommendation regarding clearing time, okay, based upon the voltage level. See, if the voltage falls below the 15% or 50% of the base voltage, the clearing time should be less than 0.16 seconds. That means immediate isolation should be there. If it is between 50% to 88%, you may disconnect yourself within 2 seconds. And if it is 110 to 120%, then you will have 1 second. If it is more than 120%, then you have to again disconnect yourself within 0.16 second. That is the clearing time available to you as per the standards. Then obviously, if frequency deviates from the base value or nominal value, again you have to have different clearing times based upon the variation in the frequency. Okay, for these recommendations are for 60 hertz. Accordingly, you may have recommendations for 50 hertz as well. And then harmonic current injection. Obviously, most of the renewable energy generations are based upon the inverters and converters. Those inverters and converters inject distortions into the system. So the harmonic or THD, total harmonic distortion, should not be more than the recommended practice or recommended limits. Okay. The local demand distortion must not be more than 5% of the local mean grade. Maximum load current integrated demand 15 or 30 minutes without the DR unit or the DR unit rated current capacity, whatever is greater. Okay. So these are the things that you should take care. Reconnection of LAPS to a main grid may occur at least 5 minutes after voltages and frequency fall within indicated required ranges. Okay. So there are a lot of things we have to take care in terms of THD, in terms of voltage magnitude, in terms of frequency. Okay. And if voltage and frequency falls below or falls outside the limit, you have to disconnect. You will have different clearing times accordingly. Other important provisions from IEEE standard about network protection, that you should connect DR in such a way that it should not cause network protection to exceed its fault interrupting capability. Okay. These are something about protection challenges. Okay. Cause it should not cause it should not cause any network protection to operate more frequently than prior to DR operation. It should not prevent or delay the network protection from opening for faults on the network feeders. It should not delay or prevent network protection closure. It should not require the network protection settings to be adjusted except by consent of the area EPS operator. It should not cause an islanding condition within part of the grid. So there are a few things those are to be taken care of in terms of network protection or existing protection system. So obviously, there will be protection challenges whenever you connect the DG. Okay. Now, what is PCC? We have discussed that the point where you connect your distributed generation or the microgrid to the main grid. Okay. Now, there is one interface that connects you to the rest of the network. Okay. This interface here is, as you can see, is power electronics interface. It is not always that you have to have power electronics based interface to connect yourself to the rest of the system. You may have several mechanical switches as well. Those can connect you to the rest of the system. And similarly, you may also have static switches. You may also have some high resistor wave switches as well. There are different classes that we are going to study and discuss next. Okay. In this diagram, you can see the components of a microgrid are a controller, several generations, and then you may also have energy storage, and then power electronic interface. Those convert the form of electric power as per the requirement of the load. There can be several loads. Those require DC supply. There can be several loads. Those require AC supply. Okay. Now, interconnection methods, as we see, those can be classified as direct through switch gears, through power electronic interfaces, and through static switches. Okay. If you connect it directly through switchgear or circuit breakers, these are quite simple and inexpensive, obviously. And obviously, they are slow enough. And since electrical characteristics of both on both sides of the circuit breaker must be the same, then electric characteristics on the microgrid side are dependent on the grid characteristics. So whatever be the voltage magnitude of the provided by the grid, that voltage is to be followed by the distributed generation and the frequency as well. Okay. For example, use of a circuit breaker implicitly limits the microgrid to have at least partially an AC power distribution system in order to match the grid's electrical characteristics. The power flow through the PCC cannot be controlled in this case. As you know, if you have a switch and it is closed, you may not have control over the power transferred from the grid to microgrid or microgrid to grid side. It can also be bidirectional depending upon the availability of the power at the local station. Okay. Now, second method, this is the circuit diagram of the first one. Then second method can be static switches, usually based on the SCRs in anti-parallel configuration. You may connect to allow bidirectional power flow. Okay. In this conventional one, which is the first one using circuit breaker, you just have to have control for this circuit breaker operation. That's it. You no need to have a control scheme for power flow. Okay. Yes. Based upon static switches, you may have anti-parallel thyristors. As you can see, the switching of these thyristors can be controlled by having a separate control mechanism that can utilize the voltages of both the sides. And sometimes you may also require the current, and that current can be obtained with the help of CTs. Okay. These are costlier and more complex than the previous method. Usually, the conventional method is still used to provide a way to achieve full galvanic isolation. Okay. You can see there will be physical isolation in previous method. A bypass switch is also added for maintenance reasons. As you can see here, one bypass switch is also available to you. Whenever you have to take it out for maintenance, you may pass the power through this bypass mode. One second, just 1 second. Okay, let me make it full screen. Yes. They allow for many open close operations. They act much faster than the conventional circuit breaker because there is no mechanical movement. And sometimes IGBTs may also be used instead of SCRs because they tend to be faster than SCRs and their current is inherently limited. Okay. So the maximum current passed through this is inherently limited, and you may also use such kind of configuration as a static switch. Still, power flow cannot be controlled. There are some conduction losses in the device as well. Okay. Then comes the power electronic interfaces. It is obviously the costlier option, but it also gives you more flexibility. Okay, in terms of power control, you may have power control, and you may also control the power going injected to the system or power drawn from the system, and you may independently control real and reactive power flow as well. And reaction times to connection or disconnection commands are similar to those provided by the static switches. Although in the case of a power electronic circuit, its response also depends on the dynamic performance given by its controller, topology, and internal energy storage component characteristics. Okay. Still, in many cases, a circuit breaker will be required at the grid side terminal of the power electronic interface in order to provide a way to physically disconnect the microgrid from the utility grid. Okay. Also, similarly to static switches, the presence of a power electronic circuit will lead to some power losses, which is not found in the approach using mechanical interfaces. Obviously, whenever you have a switching device, switching losses will also be there, okay, which was not there earlier in case of circuit breaker. Now, what are the protection challenges? But before going into this, we should also understand that what was our distribution system earlier and which kind of schemes we used to have for the protection. Okay, so ordinary protection for a distribution system is your overcurrent system, especially if you talk about the radial system. You may have different kinds of overcurrent relays. Those relays can be normally inverse, very inverse, extremely inverse, long time inverse, as well as IDEMT, and depends upon the application. You may choose any of these. The simple formula is there just to obtain the operating time of operation. You may set by altering this TMS. Okay, these alpha and beta will depend upon the characteristic which you want to have, and I is nothing but nominal current, current through the relay, and I pickup is the setting. Okay, with this you can obtain the operating time. There can be three schemes possible as we have studied already earlier: time graded, current graded, and combination of both. When you have time graded scheme, in this scheme, what is there? When you move towards the source, the operating time will increase. Okay, as you can see, if we move in this direction or towards the load, you can see earlier first setting is your 0.4 second, which is far away from the source. The middle feeder is having setting of 0.8 second, and then 1.2 second is of the relay situated close to the source or the substation. Okay. So why we have selected such kind of settings that whenever there is a fault at F3, this relay should only operate. So if the operating time of this relay is faster, then what is there? This will operate first. Once it is operated, this fault will no more be hampering the entire system, and rest of the system will be connected. Let's say if there is a fault at F2, then you have to disconnect this system and since the overcurrent will not be observed by this relay, so only this B2 will be tripped. Okay. And similarly, if there is a fault at F1, this relay will only be trimmed. Okay. So that is your time graded scheme. Then you may have current graded scheme. Again, the settings will increase in terms of current setting when you move towards the source. And this current graded scheme, the magnitude of current or the setting relay setting is corresponding to the 80% of the feeder length. Okay. Why? Because there should not be any overreach kind of condition. That means if there is a fault close to this bus, this relay may not judge that where the fault has occurred actually, because the magnitude, if the fault has occurred before the bus and after the bus, will not be different, will not be quite different. So for almost same current, this relay will take. But what should have been there, if the fault is after this bus, this relay should trip, and if it is before this relay should trip. Okay. So for that sake, we obtain these settings for 80% of the land. And if obviously if the fault is after this, after some time it will operate for that condition. Okay. So that is your current graded scheme. And then combination of both. In that situation, what you use, we prefer to use IDMT characteristic, that is the relay which you may use for this combination of time and current graded schemes. So inverse kind of characteristic will be there initially, and then the finite time will be there at the end, and that we have studied already. So that was the conventional way of protecting a feeder or the distribution system. But what are the challenges when you add distributed generation? Okay, then the first will be change in the level of fault current. As you see earlier, there was no distributed generation. The current flowing through the feeder was IGF whenever there is a fault. Okay. So whatever was the relay setting, accordingly, it will decide whether the fault is within that or not. Okay. Now, if this DG has been installed, now this current fault current will obviously increase, because there will obviously be some contribution from this as well along with this. Okay. So without DG, the fault current was IGF, and with DG, the fault current will be IGF and IDF. So the fault level has increased. Then second, bidirectional fault current can also be there. Let us consider a case when you have a fault at this bus, or which is close to the substation or the source. What will happen? There will be current supplied by this source as well as the DG. Okay. So that was the first case in which relay at R2 is having current in this direction. That is, that we may consider as reverse direction. On the other hand, if there is a fault at this location, which is after the DG, what will be there? The current supplied by this utility will have this path, and current supplied by this DG will have this path, and this relay at R2 will have the change in direction of the current. Okay. So the directional issue will also be introduced or will also be there. So with the DG integration, networks become complex and meshed, and as a result of this, the direction of fault current is bidirectional. In such a case, the relay may mal-operate. Okay. Fault tripping. You can see there are parallel feeders, and if there is a fault in feeder 1 and feeder 2 is healthy feeder at which you have connected the DG, there will obviously be some contribution by this DG to this fault. The path is also shown in the dashed one, using the dashed lines. Okay. So this relay R2 may also have that there is some fault current. If the settings are not appropriately set, this may also trip. Okay. This problem occurs when DG connected in a healthy feeder contributes to fault current adjacent to the feeder. When the fault current contributed by the DG exceeds the current setting, then relay R2 will be trimmed before the faulted feeder relay R1. So if they are not coordinated properly before the operation of this relay R1, this R2 may also trip. Okay. As a result, unnecessary power interruption will have occurred for loads connected to a healthy feeder. That means these loads will not be supplied whenever there is a fault at feeder 1. Then blinding protection, that is another thing. The main grid contribution to the fault current is decreased due to the contribution from the DG source. Okay. As you can see, if you do not have this DG connected, this IGF will be just because of this. Okay. There will be some finite magnitude of this IGF, right? But when you connect this DG, this will obviously be contributing to the fault, but simultaneously what will happen, this IGF will be reduced. That can be proved by taking the Thevenin's equivalent of this entire network, that whenever you connect the DG, this IGF contribution will be a bit reduced. Okay. And if the settings are such that it is not able to detect the fault, this relay will not be tripped. And if you have some relay situated here, this DG is disconnected, but this may sometimes be may sometimes remain connected, and that we call blinding of the protection. Okay. Then mode of operation of a microgrid. If you change the mode of operation from grid connected to grid disconnected or off grid mode, there will be decrease in the fault current. Okay. Especially in the case of inverter based DG, where fault current is restricted to twice that of the rated current. So depending on the operating modes of the microgrid, current setting of relay should be used. Okay. There can be loss of coordination, false tripping, blinding protection of a relay from the downstream to upstream feeder results in a continuous false behavior of the relay. This kind of false tripping of relays in cascaded manner is called a loss of coordination. If there is not proper coordination among the relays, relay R1 is supposed to operate, relay R2 may operate. Okay. And obviously, if the distance of the fault changes, there will be change in the fault current contribution. In a grid network with sources at the end of the network, as the impedance increases, the fault current decreases with increasing distance. For islanded microgrids with inverter-based DG, the fault current is limited to a low value. So, traditional current protection schemes that use changes in the magnitude of the fault current to differentiate may not work fine. Okay, so these are a few challenges when you connect your DG to the system, and the conventional or traditional approach of protection may be limited or may not work fine. Okay. Now coming to the islanding detection issue in a microgrid. Okay. What is islanding? Whenever the utility grid is not available, it is supposed, this network is supposed to be islanded, where you have a distributed generation and several loads. Okay. Similarly, there is another network shown by this red circle. You can see that there are two distributed generations connected and several loads connected at several buses. Okay. This is PCC2, that is corresponding to network 2. This is PCC1 here. You will have PCC1 here corresponding to this small network. Okay. So whenever this utility grid is gone, your responsibility is to operate the circuit breaker corresponding to this PCC. So what is islanding? Islanding is the condition in which distributed generator continues to power a location even though electric grid is no longer present. Okay. Microgrid allow Microgrids allow for intentional islanding. In case of an outage, the microgrid controller disconnects the local circuit from the grid on a dedicated switch and forces the distributed generation or generators to power the entire local load. Okay, that means during islanding, what will happen? This utility will not be connected, but these DGs continue to supply the local load. And what you can do if you do not have sufficient power, you may also apply load shedding, and you can also supply the critical loads. Okay, non-critical loads may be removed from the system, and only critical loads can be supplied. Now there can be intentional islanding, which is a condition in which a distributed generation continues to supply the power to the local loads during a catastrophic utility failure. Okay. With a properly coordinated and sophisticated control scheme, islanding can be the possible solution to ensure reliable power to the critical load. As I said, that whenever there is failure due to any faulty condition in the system, in the utility network, what you can do, there can be outage for several days. So what you can do, you can connect your local generation to the system and you can supply your critical load, okay, with the provision of load shedding. You can remove the non-critical loads out of the system. The concept of microgrid is still under development. For developing countries like India, distributed generation and concept of microgrid is going to play a vital role in development. But there are a lot of problems with increasing penetration of renewable energy sources in microgrid. Unintentional islanding is one of those problems. Okay, you do not know when the islanding has occurred. That can be considered as unintentional islanding. When one or more distributed resources become isolated from rest of the power system and inadvertently continue to serve loads separately from the utility system, the condition will be known as unintentional islanding. Utility engineers are seriously concerned about this kind of islanding, which is because the utility loses control over the voltage and frequency during the islanding condition. Now, there can be two things that you identify this unintentional islanding and immediately disconnect yourself. Okay, because you do not know how much load is connected and whether you will be able to supply or not if you have small generations. Okay, and if you have sufficient generations and you have control over the entire local network and you can switch several non-critical loads off, then you can remain connected to the system. Okay, so that is the point of concern, and that we call unintentional islanding. Okay, why is islanding required to be detected? That is another question. That whenever islanding occurs and there is some maintenance task that is to be taken care of by the utility workers, and they may have shocking hazard when DG remains connected to the system. They have taken shutdown from the utility, but several DGs remain connected to the system. So your distribution system will remain active and there can be shocking hazards to the utility workers. Okay. And without a strict frequency control, the balance between load and generation in an islanded mode is going to be violated, leading to abnormal frequencies and voltages. So there is an aspect of voltage stability. Whenever you are islanded, it depends upon the load and DG power mismatch, that how much mismatch is there. Accordingly, there will be variations in the voltages and frequencies. Okay, if you do not have control over the things, then there can be unstable operation. Okay, and as per the standards, and they recommend that DG is responsible to detect the islanding conditions and it is to be disconnected within 2 seconds. Okay, that is the recommendation from these standards, that you first detect the islanding and immediately within 2 seconds you disconnect yourself. Since they are assuming that you do not have control over the loads and you may not be able to have balance between the load and generation in the islanded mode. So distributed generators must detect islanding and immediately disconnect, okay, referred to as anti-islanding or islanding detection. However, DGs should be capable of operating in either of the modes. Those are grid connected mode and islanded mode with the assistance of load shedding if it is required. Okay. So summary of this is why island detection is needed. There can be safety concern and auto reclosing of the circuit breakers may fail, and eventually your circuit breaker may also damage. It may give you degraded power quality if not sufficient. There is sufficient mismatch between the load and generated power. The voltage or the frequency may deviate from the limits, and several sensitive loads may get damaged. Okay, this degraded power quality is due to converter-based DGs. They inject distortions into the system, and you have to take care of THD as well. If the THD is more than the limit, you may not remain connected. Okay, and this may also be due to the mismatch of load and generation. End user equipment may damage. Okay, if the power quality is degraded, obviously there can be damage. And to enable load shedding for islanding mode of operation, you have to detect the islanding. Okay, so these are a few reasons you should detect the islanding. Okay. Now, how to detect the islanding? There are several methods, and those can be classified into three. One, you can have local techniques. Broadly, if you classify, there will be two techniques, local as well as remote. In local techniques, there are three types, one active, another passive, and then combination of both that we call hybrid techniques. In remote techniques itself, there are three power line communication method, transfer trip method, and then SCADA based methods. Okay. These local techniques, these local techniques make use of measurement at the PCC or measurement at the DG connection, GG point of connection. Okay. In active techniques, what we do actually, we inject some kind of disturbance into the system, and then we try to observe several parameters, electrical parameters. Those parameters can be voltage, frequency, power, rate of change of power, THD, impedance, rate of change of impedance, positive sequence based parameters may also be there, negative sequence based, and like that. There are numerous parameters, those you may observe, and those may help you in obtaining the islanding detection. Okay, and then there is passive technique. In passive technique, what we do, we just make use of the local measurement and we do not intend to inject anything into the system. Okay. In active technique, we were injecting something and then based upon the response, we were deciding whether the islanding has occurred or not. However, in passive techniques, by just monitoring the measurements, we have to decide whether the islanding has occurred or not. Several passive techniques are written over here. Those are under voltage over voltage, under frequency over frequency, rate of change of frequency, rate of change of power, and then wavelength based techniques. A few techniques are written here. There are numerous passive techniques. Okay. Then hybrid techniques it makes use of both active as well as passive. They will only be injecting something into the system only and only when they see some changes into the measurements. In active techniques, what we were doing, we were injecting something continuously into the system after several seconds or so. But in hybrid technique, We will be injecting only when we see some kind of disturbances into the system. Okay, that is the only difference between the two. And then remote techniques, as we say, there are three types of remote techniques. Okay, here is the classification in a broader way. Local and remote methods are there. Local can be active, passive, as well as hybrid, which is not shown here. And then inverter based generation, you will have separate active technique. Rotating based generation, you will have separate techniques. Similarly, passive can also be classified as conventional as well as modified passive. These are the techniques, we may also call them modern techniques. In conventional, just observing voltage, frequency, rate of change of active power, rate of change of frequency, you have to decide whether islanding has occurred or not. And modified passive techniques, you may use several techniques, other techniques, feature extraction techniques. Those can be Fourier transform based, wavelet transform based, S transform based, autocorrelation function based, and Kalman filter based, and several more as well. Okay. In inverter-based generation, external signal injection, enhanced active reactive power reference, inverter resealing voltage, a few methods are also there. Several methods are also there. Similarly, for rotating based generation, there are several methods. In remote techniques, communication based, signal processing based, intelligence based. Actually, if you read a few articles, several articles, these classification will change in each of the article. Okay, there can be changes in this classification. As you saw here, power line communication, transfer tape, and SCADA. These were the classification. Here, this classification has changed. Okay. Let us discuss something about passive method. In this method, the system parameters, including voltage, current, impedance, power, or frequency, are continuously monitored at the point of common coupling. Okay. So just measuring the voltage and current will give you all these features. Say for example, voltage multiplied by current will give you power, voltage divided by current will give you impedance, and frequency can also be obtained out of the instantaneous voltage measurement. Okay, so those are the things you may easily obtain out of just CT and PT measurements. Okay, these parameters show significant variations when the main grid is disconnected from the microgrid. Okay, now this significant variation will also only be there when there is sufficient mismatch between the locally generated power and the local load. If that mismatch is not sufficient, there will not be significant variations in these parameters. Okay. The protection relays thus sense these variations and operate to trip the main breaker switch. Okay. As per the recommendation of IEEE 1547, you should detect the islanding and you should disconnect yourself within 2 seconds. Okay. The passive approaches do not affect the power quality. That is an advantage. The drawbacks of passive islanding detection methods include larger NDZ. This NDZ is nothing but non-detectable zone, a zone of power mismatch in which you may not be able to detect the islanding condition. Okay, that we will discuss later on as well. And lesser detection speed is another disadvantage or limitation of this passive method. Okay, conventional passive methods are written here. We have already discussed here as well. Okay, those are under voltage over voltage, frequency over frequency, rate of change of frequency, rate of change of power. Phase jump detection is another passive method. Now, how it works actually? Why you can say that the voltage at the PCC will deviate. Okay, consider an inverter based distributed generation. Okay, where you have connected an inverter in between and there is source of energy and inverter and then it is connected to the system. Okay, What is the capability of this inverter? That it can control the injected active as well as reactive power. So what we can assume that momentarily this PDG and QDG will not change or will not deviate whenever there is an islanding event. Okay. So this inverter has the capability of controlling PDG and QDG irrespective of the voltage at the PCC, right? Now, in this situation, what we can do, we can write the equation for PL. That PL, load power, comes from the partly from the DG as well as from the grid. So this PL is equal to PDG plus delta P, which is written here itself. PL is equal to PDG plus delta P. And this PL can be written in terms of PCC voltage as well as impedance of this load. Okay. If this active power formula you have to obtain and you are given with the PCC voltage and the load resistance, because resistance is the only element here that can consume this PL. So the formula for PL will be VPCC square divided by R, just like V square upon R. Okay. So we can equate this equal to, we can make it equal to V square VPCC square divided by R. Out of this, you can obtain the formula of VPCC. That will be square root of PDG plus delta P whole multiplied by R. Now, in this case, there are two things. One PDG, another delta P. PDG is the power supplied by the distributed generation. Delta P is the power supplied by the utility grid. Obviously, this will be the difference between the two. Okay. Now suppose there is a condition when this PDG becomes equal to PL. So whenever that is the case, this delta P will be 0 because no more supply is required from the grid to have this PL. Okay, entire PL is being supplied by this PDG. Now condition is such that delta P is 0 and on the same time, at the same time, what happens? The grid is gone. That means this S1 is open. What will happen? There will not be any change in this voltage. Since the delta P was earlier 0, after disconnection of this has to be 0. So 0 was the previous case, 0 is the next case. So there will not be any change at this in this PCC voltage. Okay. So in this case, what will happen? Your under voltage, over voltage method will fail. Okay. And it lies within the non-detectable zone where the power difference between these PDG and PL will not be sufficient enough to deviate this voltage at PCC. Okay. Similar thing will happen in case of Q or reactive power mismatch. You can see that QL will be equal to QDG plus delta Q. If you write this in terms of these reactive elements, you can write V square PCC upon XL minus XC, or XL will become omega L, XC will become 1 upon omega C. Okay. So that is quite simple. So this minus this will give you the reactive power which is consumed by the load. Okay. Out of this, you can obtain the formula or you can relate this omega in terms of this delta Q. Now again consider a case when all the reactive power demand of the load is being fulfilled by this QDG, then this delta Q is to be 0, and at the very condition, if this switch is open, there will again be 0. So earlier it was 0, now it is again 0. So there will not be any change at the frequency. So in this case as well, what will happen? The over frequency, under frequency relay will fail to detect the islanding, and again this will lie within the non-detectable zone. Okay, so that is one aspect of understanding the non-detectable zone as well as the limitation of the passive method, okay, or the over voltage under voltage method. Same thing is written here, over voltage under voltage. The conventional protection relays are installed on a distribution feeder to determine the abnormal condition during various modes of microgrid operation. These methods are based on the selective threshold value of voltage and frequency relays at common DG terminals. Okay. So again, the same thing is written at the non-zero DP. A change in the amplitude appears at PCC, which the over voltage under voltage relay detects and disconnects the DG. On the other hand, at non-zero DQ, DQ and DG is nothing but delta Q and delta. Sorry, DQ delta Q, change in reactive power, or we can say the reactive power supplied by the grid. Okay, and dP, while it is delta P. Okay, the over frequency and the frequency relay detects this change and disconnects the DG. Such a method is simple and cost effective, owing to no additional circuitry or control loops. Okay, then there is rate of change of power, rate of change of frequency. This method monitors the changes in the frequency or DG output power which appears during the islanding occurrence. Okay? When the supply of the main grid is lost, a sudden power imbalance occurs and deviates the frequency of the power system at the DG terminal. The change in frequency by considering dF by dt is measured for a shorter period of time to compare it with the stack threshold limit. If it exceeds the threshold limit, then you can say that islanding has occurred. Okay. During connected mode, it will not deviate. Okay. Usually, the tripping time for the frequency relays used in rate of change of frequency based methods should not exceed 4 to 6 cycles. Similarly, when the main utility grid is disconnected, a sudden load change is observed in the output power of the DG system. The rate of change of power method monitors the change dP by dt measured at DG terminals and integrates for a specific time interval. Compared to UV, OV, and OF/UF methods, the rate of change of power based method is fast and not affected by the small power mismatches between the DG and local nodes. Okay, but in case of over voltage under voltage, small mismatch will not give you the idea of islanding. Then there is phase jump detection method. Whenever there is an islanding, the phase of inverter will change. The output voltage will change immediately. That can be obtained. The condition can be obtained by using this formula. The NDZ of the phase jump detection method is derived using the following formula. If it is less than threshold, obviously you are not able to detect the islanding condition. It has to be more than that to detect the islanding condition. Here, this theta threshold denotes the phase jump detection phase jump threshold. The circuit reactive elements may affect the accuracy of the phase jump detection method. Therefore, it is not suitable for industrial applications. Okay, because reactive elements may affect the accuracy. Okay. Then there are active techniques. They use to inject something into the system which brings significant variations in the system parameters if it is islanded. Okay. If it is not islanded, there won't be any change in the system parameters, neither in voltage or frequency, not sufficient variation. Okay. Consequently, it triggers the relay to operate if these parameters deviate from the limits. It may cause the power quality problems and harmonic disturbances due to external signal injection. Because continuously, if you are injecting something into the system, what will happen? There will be harmonic total harmonic distortion, and that may exceed the limits which is required. Okay. Active islanding detection methods are mostly developed for inverter-based DG systems because you have the control over the injections. You can have injections in terms of voltage perturbation, current perturbation, power perturbation, similarly change in phase, like that means you can have control over the injections. So that is mostly for the inverter based DGs. Given that synchronous DGs may deviate the frequency control over or reactive power output by frequency or reactive power output by inducing a destabilization error upon islanding. Active islanding detection methods use intelligent relays and more efficient algorithms. Okay, that is for synchronous based DGs. Some of the examples are impedance measurement, active frequency drift, Sandia frequency shift, Sandia voltage shift, sliding mode frequency shift. We will see a bit of each. Impedance measurement means you will first inject something into the system and you will see the variation, you will observe the variations in the high frequency impedance. Okay. This impedance is obtained from the voltage and current measurements. It becomes more significant during the islanding condition. However, during non-islanding condition, it will not deviate much. Okay, it will not have sufficient variations. It is mostly used for the power systems comprising of synchronous based distributed generation. And it obviously we have a small non-detectable zone. If you compare it with the voltage and frequency based methods, it will be negligible. Okay. For the systems comprising single inverter based DG and local loads having a larger impedance than the main utility grid impedance. Okay. Injection of high frequency signal produces voltage and current harmonics. Obviously, it will affect the performance of the such methods. The threshold selection in this method is also a difficult task because it can be affected due to the strength of the injected signal. Okay, so depending upon the circuitry and the rest of the things, you have to decide the threshold. Then comes the active frequency drift method. It utilizes a slightly distorted inverter current waveform that is injected into the PCB. Say for example, if the current injected by the inverter is 10 ampere, you may inject perturbation into that current after 2 seconds, after each 2-second intervals. Say 10 ampere is the current, you may inject a disturbance of say 0.1 ampere. Okay, so each time what will be there? There will be pulse kind of thing after 2 seconds. Okay, 10 ampere is running magnitude and suddenly it will become 10.1 or 9.9. So that kind of disturbance will be injected, and in grid connected operation, voltage and frequency will not deviate owing to the grid stability, because grid is taking care of the voltage and frequency both. Okay, when the grid is disconnected, a zero crossing of the voltage occurs due to the perturbing signal injection that gives rise to the phase error between the output voltage and the inverter current. Based upon this phase error, a frequency drift will be there, and that can be observed to eliminate the which eliminates the phase error. Okay, this frequency drift originates another zero crossing until the voltage frequency exceeds the predefined threshold limit. Thereby, you can detect the islanding condition. Okay. The performance characterization of active frequency drift method describes the relation between inverter current distortion and the load resonance frequency based upon this equation. Okay. In this equation, omega is the frequency of the inverter, Cf is the chopping fraction, and Tz is nothing but zero or that time of the active frequency drift. Then comes the Sandia frequency shift. In this method, this is actually an extension of the previous method. where a positive feedback is applied to the inverter voltage frequency with a connection to the utility grid. That means you are measuring something at PCC, that is your voltage frequency, and the positive feedback is given to the inverter. And whenever the grid is gone, there will be the changes in the frequency introduces an inverter phase error, which continues until the frequency exceeds the predefined threshold limit. That means due to positive feedback, if there is any phase angle error, that phase angle error will increase continuously, and at a point of time it will exceed the threshold limit, and at that point of time you can say that islanding has occurred. For this method, an appropriate selection of parameters such as chopping frequency, accelerating gain is an essential task that significantly affects the overall detection performance. Okay, the inverter phase angle and SFS parameters are expressed as follows, where the terms are being defined as written. Sliding mode frequency shift method, it uses phase angle of the inverter output current, okay, which is controlled as a function of terminal voltage frequency. This method utilizes positive feedback again to change the phase voltage. Okay, now it is changing the phase voltage at the DG terminals by monitoring the frequency deviation and thus detecting the islanding condition. Okay. The change in the phase angle of the inverter output current is always relative to the grid output voltage. Thus, the frequency of the grid voltage deviates from its nominal value whenever the utility grid is disconnected. The phase angle perturbation sometimes lead to the measurement or quantization error, which is addressed through the introduction of the improved sliding mode frequency shift method. Then comes the Sandia frequency shift. In this method, what is there? A positive feedback is applied to the voltage amplitude this time at the output terminals of the DG unit or PCC. In the grid connected mode, there will be negligible effect on the power system. However, whenever it is disconnected mode, a significant reduction at the PCC voltage will be observed. Okay. Anti-islanding protection relays detect the reduction and send the tripping to the DG. Okay, so that the output of the DG can be seized over. The SVS method, which is Sandia frequency voltage shift method, is known to be the most efficient method among other feedback-based detection methods. Okay, by combining the merits of SVS and SMS, a more efficient detection method can be developed, which might not affect the power quality and may perform well. Then comes the remote techniques. See, these remote techniques require installation of signal generators at the utility side and receiver at the DG side. Okay, and installation of those things make this quite costlier, and it is not an economical way of detecting the islanding. Rather, other methods are preferred. Okay. The remote techniques are based on the communication links between the utility grid and DG sources. These methods perform efficiently and have negligible NDZ. And NDZ is defined as the range of operation of operational power region that is not protected by conventional protection devices. Okay. Although remote techniques have better reliability than local islanding detection methods, they are uneconomical. Okay, because higher cost, high computational burden, and complexity are the main drawbacks of communication-based islanding detection methods. Okay, in this technique, the main grid and DG units share the information using a communication channel, and based upon that thing, there can be several further classifications. Okay, Islanding detection is mainly based on the information collected from the applied media and sent to the tripping switch. Common examples are power line communication, SCADA system, and then transfer trip method. Okay. So in this diagram, you can see you have to install a signal generator that can be considered as a transmitter and a receiver at the DG side, so that the signal can be sent from this and can be received here, and that signal will consist of the information whether the islanding has occurred or not. The PLC method detects the islanding condition using the communication signal through the power lines itself. In this method, a transmitter device sends a continuous low voltage signal to the microgrid or DG side using power line carriers that are equipped with a receiver device. Okay. Usually, the sending signal is designed with 4 consecutive cycles, and the islanding condition is detected if the signal disappears for a few cycles. Okay. It is not suitable for large-scale integrated power network due to the increasing cost and other complexities. Okay. Then transfer trip method. Usually, this method is integrated with the SCADA system to monitor the operating switches while providing an efficient coordination between the microgrid and main grid. Such methods have negligible anti-jet, and obviously the islanding detection will be faster. However, this method has hardware limitations, high cost, and risk of communication failure. Then comes the SCADA system. It actually monitors a lot of uh, signals at a lot of different buses actually, and based upon the collection of that data, you may decide. Okay, and the islanding phenomenon occurs, the grid parameters are suddenly altered, and thus the audible alarm starts ringing and the relays operate to disconnect the DG source. Moreover, the implementation of SCADA systems guarantees a synchronized operation of the microgrid and utility grid to avoid any phase difference. Okay. In addition, it provides easy restoration after the disappearance of the disturbance. Now there are modified passive techniques. As we saw that conventional passive techniques have the limitation of non-detectable zone. Okay. The idea of modified passive techniques is to reduce that non-detectable zone as much as possible. These modified techniques are nothing. They give you several additional features. Those features can be in terms of frequency, spectrum, different spectrum, and several other parameters, say high frequency impedance, okay, and like that. The application of well-known time domain, frequency domain, and time frequency domain signal processing tools have helped the researchers to improve the existing islanding detection schemes and develop new methods such as Fourier transform, wavelet transform, S transform, time transform, autocorrelation function, Kalman filter. Okay, these helps these help to analyze and extract the important features of a measured signal in order to perform efficient power system operations. Okay. In Fourier transform, it is a frequency domain analysis tool that extracts the features of a signal at the specified frequencies. Okay. Say there can be different frequency components present in the signal, and out of those frequency components, you will be interested in some particular frequency ranges. Okay, so those frequency ranges can be obtained by using this kind of method. Okay, researchers have utilized such tools to develop efficient and fast islanding detection methods. Besides several advantages, there is a certain limitation, including reduced spectral estimation and low frequency resolution. This low frequency resolution problem has been mitigated using the wavelet transform based methods. Okay, that gives you better resolution. Okay. Methods based on wavelength are associated with STFP and the multi-resolution techniques. Okay. If these coefficients attain a larger value than the predefined threshold value, the islanding, the islanding condition will be detected. Okay. This can extract significant features from a measured voltage or current signal using approximation and detailed decomposition. Then there is S transform based method. The spectral energy content of these contours is calculated as containing the information of frequency and magnitude deviations for islanding detection. Okay. To process a signal, the ST method requires more computational memory than the other similar techniques. Okay. Moreover, the processing time of such methods is large. Then comes the time transform based method. The TTD method analyzes and transforms a one-dimensional time domain signal into two-dimensional time domain signal by giving time distribution on a particular window. Okay. In this method, a low frequency components are concentrated at different positions, whereas the high frequency components are concentrated around the localization point, having more energy concentration. And based upon that, you can identify the islanding situation. They show good performance in the noisy environment. And then autocorrelation function. This is a mathematical tool used to extract the hidden information from a measured power and energy signal. While considering the finite duration sequences, it is expressed using the finite summation limits. The method uses the calculated envelopes derived by the Hilbert transform to extract transient features for which the variation of samples provides the criterion for islanding detection. Okay. Then there is Kalman filter as well. It will also give you some kind of a feature. The islanding condition is classified using the residual signal, whereas the SHD, that is selected harmonic distortion, is used for the detection purpose in a timely manner. Then comes the intelligent methods. They can be based upon ANN, decision tree, TNN, SVM, fuzzy logic, etc. Okay. There can be training. If you talk about intelligent methods, first you have to train and then you may apply. While fuzzy logic based method, that is rule based method, and you should have better information about the system. And accordingly, you may design several rules, and those rules will help you in identifying the islanding. What are the processes in these intelligent methods? One is your offline process, another is your online process. In offline process, what you do, it is basically your training. You train this network offline, and then when apply, that will be called online process. Okay. And different methods of detection based upon their features. What are the merits and demerits? What will be the computational burden? What will be the detection speed? How much non-detectable zone will be available? So based upon that, here is the classification, and you can see that in local methods, active methods may have small NDZ, while passive methods, they can be large for case of conventional one. For modern techniques, there will be small NDZ, while remote techniques will have negligible non-detectable zone. In terms of computational burden, you can see active techniques will give you will require medium computational burden, while passive will have negligible burden, and remote techniques will be mostly will place high burden on the in terms of computation. Okay. Then detection technique speed. Active technique will be will have medium detection technique, while passive method will have low and high. If it is conventional, we'll have low detection speed. If it is modified or modern one, we'll have high detection speed, while that or remote techniques will have higher detection speed. Okay. Then based upon several standards. What are the requirements in terms of detection time, allowed frequency ranges, allowed voltage ranges? Okay, as you can see, that Korean standard gives you clearing time which is less than 0.5 seconds, sorry, detection time which is less than 0.5 seconds, while that of other standards, it is less than 2 seconds. Okay, and this frequency is corresponding to again 60 hertz, and this is voltage is given in per unit. Whenever you have 0.88 to 1.1 per unit of the voltage, nominal voltage, you need not to worry about. It can be considered as a normal condition, and that is nearly applicable for all the standards. Now, how to analyze the performance of any islanding detection method? Okay, there are three things: one, non-detectable zone, and parallel RLC load, and the load quality factor. Okay, so these are the three main performance indices that characterize the operational capability of any islanding detection method. Okay, if a method successfully detects the islanding condition under such circumstances, the superiority of the method is highlighted and is satisfied by the international standard. Okay. How to obtain the non-detectable zone? That you can obtain using the two formulas, and that non-detectable zone is visible here. Whenever this delta Q and delta P, they lie within this shaded region, the technique is not able to detect the islanding. Okay. In this region, what is there? This delta Q and delta P will be very small. Okay, that means grid is not supplying any reactive power or supplying very less of reactive power. Similarly, very less of the active power. And during such region, in this region, you may not be able to detect the islanding. And how you model the parallel RLC distributed load? We model it as parallel RLC load. Most of the loads in power systems are inductive in nature, where inverter-based DG units mostly operate at unity power factor to produce maximum kilowatt hour. Such a condition, in combination with the parallel RLC load, is considered as a worst case scenario to detect the islanding. And it is considered that load is also having unity power factor. If that is the condition, as per UL 1741 standard or detection criteria, that can be considered as worst possible condition. And if you are able to detect under such condition, your detection technique will be considered as an excellent method. Okay, it is similar to the previous diagram where you can see delta P, delta Q is the grid supplied reactive and active powers, while P and Q in this case is power supplied by the PG, and then the net power will go to the load. Okay, so in this equation, these are the powers written. Parallel RLC load from previous equation, BPCC is clearly dependent on the active power that we have seen earlier as well. And similarly, the deviation in the frequency at the PCC for the DG system operating at a unity power factor will be observed if the load on the islanded system absorbs the reactive power. Okay, if it is not absorbing, there won't be any change in the frequency. The load inside the islanded system possesses a high quality factor due to the varying characteristics of resistances, inductances, and capacitances. Therefore, the parallel RLC loads with a high quality factor often create technical challenges during the islanding detection process. Okay, so the load for quality factor formula is written over there. The load quality factor affects the size of the NDZ and detection accuracy. And therefore, the performance analysis of any method significantly depends on the value of the load quality factor. Assuming it to be 2, there is twice as much energy stored in the inductor or capacitor as the load of the load as is being dissipated in the resistor. That is the physical significance of the QF that we all know. And mathematically, the quality factor can be defined as QF is equal to R square root C over L. From the above discussion, the size of NDZ significantly depends on the value of QM, but is relative to the active and reactive power mismatches. And again, there is comparison. The previous diagram is once again you can see in a modified version. Now, what to do after islanding detection? As I said, there are two options available to you. Either you remain connected to the system or you disconnect yourself. So, IEEE 1547 standard says that please disconnect yourself within 2 seconds, and they assume that distribution system becomes passive after this disconnection, and no reclosing problem will be there. Okay, so as per the recommendation of the IEEE standard, these are the two factors they consider, that if you are able to detect the islanding and disconnect yourself within 2 seconds, there won't be any such problem. Okay. Second option is you may remain connected, and which is preferable actually, that will give you full utilization of the resources. Okay. Voltage and frequency of the PCC are to be controlled by you independently, and you may also apply load shedding, and critical loads can be given the priority. Okay. Now, what are the sequences? Okay. First, you have to detect the grid loss. Second, you have to assess loads and shed if needed. You may disconnect several loads if it is required, and accordingly you can prioritize the loads and bring on idle spare generation capacity. If you have several other generating capacity, you connect them to the system, share and then share power to the loads. Okay, just like this. So if you have diesel generator backup, you connect it, begin islanded operation. Okay, then you can begin the islanded mode of operation and complete it within 50 milliseconds. And in this process, if you also have the battery energy storage or several other energy storage system, it may provide you stabilization. Okay. Then you can summarize it that rather than going for bulk power generating stations, we can have several small distributed generations. Those are connected at the local level or close to the loads. And while doing so, you are actually uh, reducing the transmission losses, and that gives you a lot of economical advantages. With this, when you have such kind of provisions, the challenges will be in terms of protection as well as islanding issue. Okay, protection challenges can be the power flow can be bidirectional, there can be blinding of protection, there can be change in fault current level, and there can be false operation of the relay. Okay, so such kind of challenges in terms of protection can be there. If you talk about islanding phenomenon, you have to detect unintentional islanding, and accordingly you can change the mode of operation if you want to remain connected. Or what you can do, once you detect the islanding, if you are not able to supply the local load, you disconnect yourself from the system. Okay, so that is from the today's discussion. Over to you, ma'am. Any questions, please? Yes, yes, ma'am. Yes, ma'am. Please. Okay. Thank you, ma'am. Thank you so much.